We review vectors in Calculus 3, and this is another problem that shows up in that class. So it says here the graph shows two forces pulling on an object at the origin, each of 10 newtons of magnitude. So I have the vector u pulling at the origin at 30-degree angle from the vertical, vector v pulling at an angle 45 degrees from the vertical, and each one is length 10. All right. Now, what is the direction and magnitude of the resultant force? So let's make a conjecture about where that would be. If I pulled on this one at 10 newtons and someone else pulled on this one at 10 newtons and there was an object here, where would it go? Well, because of the way that it's shaped, it looks like it's going to go somewhere in the middle here. If I drew my little parallelogram, making the v parallel with this side and the u parallel this side, the resultant vector should come right up here in the middle, and that's where I want it to be. So it should be in the first quadrant with both I and j components being positive. Now, if I want the resultant force, that is going to be just taking the vector u and adding it to the vector v. In order to do that, the best way is to find the components of v and u. Now, I know that this angle here is 45 degrees, and I know that this angle here is 60 degrees. So I'm going to use some trigonometry and some quadrants, information about sines and quadrants, and I'm going to come up with components for u and v. So let's start with v. So since the magnitude of this guy is 10, I know the length of this I component here is going to be cosine 45 degrees times 10. So 10 cosine 45 degrees. That's my I component. Plus my j component is going to be 10 times the sine of 45 degrees. If I just simplify that, I get 10 times square root of 2 over 2i plus 10 times the square root of 2 over 2j using, the unit circle, exact values, standard angles, etc., etc. So I get a lovely vector, and I want to put it in this notation here. 5 square root of 2 I component and 5 square root of 2 j component, which makes sense because with a 45-degree angle, the I and j should be the same components, same length. If I do the same thing for u, now this is in the second quadrant, so the I component, I'm just going to use the same idea here, but the I component is going to be j, or negative, sorry, I component is negative and the j component is positive. So I'm going to have negative 10 cosine of 60 degrees for I, and then 10 sine of 60 degrees for j. That's going to give me negative 10. The cosine of 60 is 1/2. Look it up if you don't know. Plus 10 sine of 60 is square root of 3 over 2j. So writing it in the other notation, I get minus 5 square root of 3. So then in the end, to get my resultant vector, I have to add u plus v. That's going to be minus 5 square root of 3, plus 5 square root of 2, 5 square root of 2. Now, remember when you add vectors, you have to add like components. So I have to add the i's together. And I have to add the j's together. Let's put those in the calculator. See what number we get. So I have minus 5 plus 5 square root of 2. So it's 2.0711. 2.0711. And the j component is 5 square root of 3 plus 5 square root of 2. And that gives me 15.7313. Now, if I want to make sure that's right, so according to this, I have to go just 2 units on the x-axis here, just 2 units, and then 15 units up, which puts it right in that spot where I want it to be. So this vector, u plus v, is going to be the resultant force. Now part B says, what is the direction and magnitude of the force that will keep the object at the origin in its original place? Well, if I want to keep the object at the origin in its original spot, the sum of all the forces have to equal 0. So that means that u plus v plus my new vector that's going to be pointing down in this direction, down this way, has to equal the 0 vector. So I already have u plus v is 2.0711, comma 15.7313, but I have to add it to the vector a to get the 0 vector. Well, that means that a is just going to be the opposite direction of my u plus v. So a is equal to negative 2.0711, negative 15.7313. That's going to keep the object fixed if I pull directly in the opposite direction of the vector that was here, which puts this guy in quadrant 3, it looks like. Now, that's not the answer to the question. The question says the direction and the magnitude. Direction and magnitude. So if I go down to quadrant 3 and I draw this guy out right here, I have a vector that comes down like this. I know that this is negative 15.7313. I know that this is negative 2.0711. What I'm looking for is this angle here, alpha, and I'm looking for the length or the magnitude of A. Now, if you can see this, I can see the Pythagorean theorem going on here. The magnitude of A is just the square root of those two guys squared. So let's do that one first. The magnitude of A is equal to the square root of minus 2.0711 squared plus minus 15.7313 squared. That'll give me my magnitude, which is really important if I want to find that angle right there. So the magnitude needs to be done first. So if I do the magnitude, second square root, negative 2.0711 squared. Well, let's do the parentheses in here and then square it. Plus negative 15.7313 squared. Close off the parentheses that started right there, and I should get my magnitude. 15.8670 units. 15.8670. So if I think about a circle that's coming around here, I'm dealing with a circle that has a radius of 15.8670. So that length, 15.8670, has a lot to do with my angle alpha. So according to trigonometry, I know that the angle alpha, let's see how this works. I know that 15.8670 times the cosine of alpha should equal this length right here, 2.0711. Now you're probably saying to yourself, well, why not the negative? Where's the negative? Well, if I put the negative on there, that's going to give me this whole angle rotation all the way from here. I just want this acute angle right there. So I'm thinking of everything in terms of positive. Because that acute angle, alpha, if I want to know the direction, that's going to be, alpha is going to go, let's see, alpha degrees south of west. Okay, so if I can just get that acute angle, then I know the direction, alpha degrees south of west. Where does this come from? Well, there's a known thing that says that my x-coordinate is going to be r cosine theta from trigonometry. So I have my x-coordinate, r cosine, and theta is my alpha here, and that's where this comes from. This is from trigonometry. All right, let's keep going. Let's solve for alpha. So cosine of alpha is going to be 2.0711 divided by 15.8670. So 0.1305. Did I write that down right? 1305. All right, so that means alpha is going to be the cosine inverse of that. Cosine inverse of my answer, 82.4999 degrees. Now, does that make sense? So 82 degrees is almost to 90 degrees, so that would leave this angle here really tiny. So that makes sense, 82.499 degrees. So now if I answer the question, what is the direction and magnitude of the force? So the direction and magnitude, let's see, vector A should be pointing in the direction of 82.4999 degrees south of west with a magnitude of 15.8670. Now, there may be a variety of ways to do this problem, but this is the one that uses the most information from your past without having to come up with any tricks or stuff from an online web source or something like that.